Public keys. An Ethereum public key is a point on an elliptic curve, meaning it is a set of x and y coordinates that satisfy the elliptic curve equation. In simpler terms, an Ethereum public key is two numbers joined together. These numbers are produced from the private key by a calculation that can only go one way. That means it is trivial to calculate a public key if you have the private key, but you cannot calculate the private key from the public key. Warning: math is about to happen. Don't panic. If you start to get lost at any point in the following paragraphs, you can skip the next few sections. There are many tools and libraries that will do the math for you. The public key is calculated from the private key using elliptic curve multiplication, which is practically irreversible. Big K equals small k times big G, where small k is the private key. Big G is a constant point called the generator point, big K is the resulting public key, and times is the special elliptic curve multiplication operator. Note that elliptic curve multiplication is not like normal multiplication. It shares functional attributes with normal multiplication, but that is about it. For example, the reverse operation, known as finding the discrete logarithm, i.e. calculating small k if you know big K, is as difficult as trying all possible values of small k, a brute force search that will likely take more time than this universe will allow for. In simpler terms, arithmetic on the elliptic curve is different from regular integer arithmetic. A point, big G, can be multiplied by an integer small k to produce another point big K, but there is no such thing as division. So it is not possible to simply divide the public key big K by the point big G to calculate the private key small k. This is the one-way mathematical function described in public key cryptography and cryptocurrency. Note, elliptic curve multiplication is a type of function that cryptographers call a one-way function. It is easy to do in one direction and impossible to do in the reverse direction. The owner of the private key can easily create the public key and then share it with the world, knowing that no one can reverse the function and calculate the private key from the public key. The mathematical trick becomes the basis for unforgeable and secure digital signatures that prove ownership of Ethereum funds and control of contracts. Before we demonstrate how to generate a public key from a private key, let's look at elliptic curve cryptography in a bit more detail. Elliptic curve cryptography explained. Elliptic curve cryptography is a type of asymmetric or public key cryptography based on the discrete logarithm problem as expressed by addition and multiplication on the points of an elliptic curve. A visualization of an elliptic curve is an example of an elliptic curve, similar to that used by Ethereum. Note, Ethereum uses the exact same elliptic curve called SECP256K1 as Bitcoin. That makes it possible to reuse many of the elliptic curve libraries and tools from Bitcoin. Ethereum uses a specific elliptic curve and set of mathematical constants as defined in a standard called SECP256K1, established by the U.S. National Institute of Standard and Technology, NIST. The SECP256K1 curve is defined by the following function, which produces an elliptic curve. Y squared mod p equals x cubed plus 7 mod p. The mod p indicates that this curve is over a finite field of prime order p, where p equals 2 to the 56 minus 2 to the 32 minus 2 to the 9th minus 2 to the 8th minus 2 to the 7th minus 2 to the 6th minus 2 to the 4th minus 1, which is a very large prime number. Because this curve is defined over a finite field of prime order instead of over the real numbers, it looks like a pattern of dots scattered in 2 dimensions, which makes it difficult to visualize. However, the math is identical to that of an elliptic curve over real numbers. As an example, elliptic curve cryptography, visualizing an elliptic curve over f of p, with p equals 17, shows the same elliptic curve over a much smaller finite field of prime order 17, showing a pattern of dots on a grid. The SECP256K1 Ethereum elliptic curve can be thought of as a much more complex pattern of dots on an unfathomably large grid. So, for example, the following is a point Q with coordinates x, y, that is a point on the SECP 256K1 curve. Q equals 4979 comma 595 360. Example 1 below shows how you can check this yourself using Python. The variables x and y are the coordinates of the point Q, as in the preceding example. The variable p is the prime order of the elliptic curve, the prime that is used for all the modulo operations. The last line of Python is the elliptic curve equation. The percent operator in Python is the modulo operator. If x and y are indeed the coordinates of a point on the elliptic curve, then they satisfy the equation and the result is 0. 0L is a long integer with value 0. Try it yourself by typing Python on a command line and copying each line from the listing. Python 3.4.0 P equals 115 663, x equals 497 515, y equals 595 360. X cubed plus 7 minus y squared. Modulo p produces the output 0. Elliptic curve arithmetic operations. A lot of elliptic curve math looks and works very much like the integer arithmetic we learn at school. Specifically, we can define an addition operator, which instead of jumping along the number line, is jumping to other points on the curve. Once we have the addition operator, we can also define multiplication of a point and a whole number, which is equivalent to repeated addition. Elliptic curve addition is defined such that given 2 points P1 and P2 on the elliptic curve, there is a third point, P3 equals P1 plus P2, also on the elliptic curve. Geometrically, the third point, P3, is calculated by drawing a line between P1 and P2. This line will intersect the elliptic curve in exactly one additional point, amazingly. Call this point P3 prime equals x comma y. Then reflect in the x-axis to get P3 equals x comma negative y. If P1 and P2 are the same points, the line between P1 and P2 should extend to be the tangent to the curve at this point, P1. This tangent will intersect the curve at exactly one new point. You can use techniques from calculus to determine the slope of the tangent line. Curiously, these techniques work, even though we are restricting our interest to points on the curve with two integer coordinates. In elliptic curve math, there is also a point called the point at infinity, which roughly corresponds to the role of the number 0 in addition. On computers, it's sometimes represented by x equals y equals 0, which doesn't satisfy the elliptic curve equation, but it's an easy separate case that can be checked. There are a couple of special cases that explain the need for the point at infinity. In some cases, for example, if P1 and P2 have the same x values, but different y values, the line will be exactly vertical, in which case P3 equals the point at infinity. If P1 is the point at infinity, then P1 plus P2 equals P2. Similarly, if P2 is the point at infinity, then P1 plus P2 equals P1. This shows how the point at infinity plays the role that 0 plays in normal arithmetic. It turns out that plus is associative, which means that a plus b plus c equals a plus b plus c. That means we can write a plus b plus c without parentheses, without ambiguity. Now that we have defined addition, we can define multiplication in the standard way that extends addition for a point P on the elliptic curve. If k is a whole number, then k times p equals p added to itself k times. Note that k is sometimes, perhaps confusingly, called an exponent in this case. Generating a public key. Starting with a private key in the form of a randomly generated number k, we multiply it by a predetermined point on the curve called the generator point g to produce another point somewhere else on the curve, which is the corresponding public key big K. big K equals small k times big G. The generator point is specified as part of the SECP256K1 standard. It is the same for all implementations of SECP256K1, and all keys derived from the curve use the same points, big G. Because the generator point is always the same for all Ethereum users, a private key small k multiplied with big G will always result in the same public key, big K. The relationship between small k and big K is fixed, but can only be calculated in one direction, from small k to big K. That's why an Ethereum address derived from big K can be shared with anyone and does not reveal the user's private key, small k. As we described in the previous section, the multiplication of small k times big G is equivalent to repeated addition, so big G added to itself k times. In summary, to produce a public key, big K, from a private key, small k, we add the generator point big G to itself k times. Tip: a private key can be converted into a public key, but a public key cannot be converted back into a private key, because the math only works one way. Let's apply this calculation to find a public key for the specific private key we show you in the private key section. Example private key to public key calculation. Big K equals f8f8 times big G. A cryptographic library can help us calculate big K using elliptic curve multiplication. The resulting public key, big K, is defined as the point big K equals x comma y, where x equals 6e14.07b, y equals x3b cd0. In Ethereum, you may see public keys represented as a serialization of 130 hexadecimal characters, 65 bytes. This is adopted from a standard serialization format proposed by the Industry Consortium Standards for Efficient Cryptography Group, SECG, documented in Standards for Efficient Cryptography, SEC1. The standard defines 4 possible prefixes that can be used to identify points on an elliptic curve, listed in the table below. Ethereum only uses uncompressed public keys, therefore the only prefix that is relevant is hex 04. The serialization concatenates the x and y coordinates of the public key, 04 plus x coordinates plus y coordinates. Therefore, the public key we calculated earlier is serialized as 046e1 cd0. Elliptic curve libraries. There are a couple of implementations of the SECP256K1 elliptic curve that are used in cryptocurrency-related projects. 1. OpenSSL. The OpenSSL library offers a comprehensive set of cryptographic primitives, including a full implementation of SECP256K1. For example, to derive the public key, the function EC_point_mul can be used. 2. libSECP256K1. Bitcoin Core's libSECP256K1 is a C language implementation of the SECP256K1 elliptic curve and other cryptographic primitives. It was written from scratch to replace OpenSSL in Bitcoin Core software and is considered superior in both performance and security. Cryptographic hash functions. Cryptographic hash functions are used throughout Ethereum. In fact, hash functions are used extensively in almost all cryptographic systems, a fact captured by cryptographer Bruce Schneier, who said, "Much more than encryption algorithms, one-way hash functions are the workhorses of modern cryptography." In this section, we will discuss hash functions, explore their basic properties, and see how those properties make them so useful in so many areas of modern cryptography. We address hash functions here because they are part of the transformation of Ethereum public keys into addresses. They can also be used to create digital fingerprints, which aid in the verification of data. In simple terms, a hash function is any function that can be used to map data of arbitrary size to data of fixed size. The inputs to a hash function is called a preimage, the message, or simply the input's data. The output is called a hash. Cryptographic hash functions are a special subcategory that have specific properties that are useful to secure platforms, such as Ethereum. A cryptographic hash function is a one-way hash function that maps data of arbitrary size to a fixed size string of bits. The one-way nature means that it is computationally infeasible to recreate the input data if one only knows the output hash. The only way to determine a possible input is to conduct a brute force search, checking each candidate for a matching output. Given that the search space is virtually infinite, it is easy to understand the practical impossibility of the task. Even if you find some input data that creates a matching hash, it may not be the original input data. Hash functions are many-to-one functions. Finding two sets of input data that hash to the same output is called finding a hash collision. Roughly speaking, the better the hash function, the rarer hash collisions are. For Ethereum, they are effectively impossible. Let's take a closer look at the main properties of cryptographic hash functions. These include 1. Determinism. A given input message always produces the same hash output. 2. Verifiability. Computing the hash of a message is efficient, linear complexity. 3. Non-correlation. A small change to the message, for example a 1-bit change, should change the hash output so extensively that it cannot be correlated to the hash of the original message. 4. Irreversibility. Computing the message from its hash is infeasible, equivalent to a brute force search through all possible messages. 5. Collision protection. It should be infeasible to calculate two different messages that produce the same hash output. Resistance to hash collisions is particularly important for avoiding digital signature forgery in Ethereum. The combination of these properties make cryptographic hash functions useful for a broad range of security applications, including 1. Data fingerprinting, 2. Message integrity, error detection, 3. Proof of work, 4. Authentication, password hashing and key stretching, 5. Pseudo-random number generators, 6. Message commitment, commit review mechanisms, 7. Unique identifiers. We will find many of these in Ethereum as we progress through the various layers of the system. Ethereum's cryptographic hash function, catcheck 256. Ethereum uses the catcheck 256 cryptographic hash function in many places. Catcheck 256 was designed as a candidate for the SHA-3 cryptographic hash function competition held in 2007 by the National Institute of Science and Technology. Catcheck was the winning algorithm, which became standardized as Federal Information Processing Standards (FIPS) 202 in 2015. However, during the period when Ethereum was developed, the NIST standardization was not yet finalized. NIST adjusts some of the parameters of catcheck after the completion of the standard process, allegedly to improve its efficiency. This was occurring at the same time as heroic whistleblower Edward Snowden reviewed documents that implied that NIST may have been improperly influenced by the National Security Agency to intentionally weaken the dual ECDRBG random number generator standard, effectively placing a backdoor in the standard random number generator. The result of this controversy was a backlash against the proposed changes and a significant delay in the standardization of SHA-3. At the time, Ethereum Foundation decided to implement the original catcheck algorithm as proposed by inventors rather than the SHA-3 standard as modified by NIST. Warning: while you may see SHA-3 mentioned throughout Ethereum documents and code, many, if not all, of those instances actually refer to catcheck 256, not the finalized FIPS 202 SHA-3 standard. The implementation differences are slight, having to do with padding parameters, but they are significant in that catcheck 256 produces different hash outputs from FIPS 202 SHA-3 for the same inputs.